Hi everybody, it's Brian. We're going to talk about curve sketching and look at some techniques from calculus you can use to help you get a sense of what the graph of some function looks like without putting into a software like a graphing calculator or something like that. I know this is kind of an old-timey type of activity. In some sense, you don't need to be able to do this because it's so easy to graph it with software nowadays. But still, it's good to be able to kind of think about a function and have a sense of what it looks like. And because just developing an intuition about how the numbers relate is just going to be helpful for making you more numerate generally. Anyway, we'll talk through it, but as you'll see, it's easy to check your work using software. So when you're graphing functions, you can use some of these points to help you get an idea of what it would look like. So first of all, you should know what the domain is of the function, or what the interval that you're looking at is. And if there's any symmetry with this function, if it was an even function or an odd function, for example, you should note that. Then find critical points and inflection points. So you're going to find the first derivative and the second derivative and see if you can find the critical points from the first derivative where it's equal to 0 or where the first derivative doesn't exist. And the inflection points are where the second derivative is equal to 0, where the curvature changes from upward curvature to downward curvature. Then finding the extreme values of the function, if there's minimums and maximums, and any asymptotes, the end behavior as x goes to infinity or to negative infinity. There's a bit of a typo there. I'll make a little note. Okay. And then finally, the intercepts are going to be helpful. So let's take a look at some examples. Okay, let's take y equals 2x squared. So first off, you looking at this, we can see the domain is going to be as long as x squared minus 1 is not equal to 0. So that's actually x, as long as x is not equal to minus 1 or plus 1. So those are going to be the kind of holes in the domain. So let's, I'll try to sketch this thing out a little bit just to start out with. Put some axes down, and we'll note that we have asymptotes. This is a rational function at -1 and +1. What else can we say? We know we can identify the x-intercept. The x-intercept, when you can see that when this function is going to be 0 only when x is equal to 0. So in fact, the point 0, 0 is going to be the one and only x-intercept. So I can actually plot that point there. Now let's think about. And you can see also that, well, let's put the asymptotes in. So when x, the limit as, let's put it like this, the limit as x goes to infinity of 2x squared over x squared minus 1. So when x gets really, really big, you can see this is going to be going to 2. You could use L'Hopital's rule, or you could just remember about limits, because the degree of the polynomial in the numerator and the denominator are both degree 2. So you just look at the ratio of their intercepts. And then the same thing goes for, that's also the limit as x goes to negative infinity of 2x squared over x squared minus 1. I'm getting a little weird with my x. Okay. So this is the asymptote, and now we can take a look at the, let's find the derivative. Y prime is going to be 4x times x squared minus 1 minus 2x squared times 2x. That's the derivative of that. So actually, this is going to be 4. This is that's all over x squared minus 1 squared. This thing is only equal to 0 when the numerator is equal to 0. And if you work that out, it's 4x to the third minus 4x minus 4x to the third. So it turns out that this is just equal to negative 4x. Oh, I'm sorry, to the third. So if you take values of x, you can see that when x is 0, this thing levels out because that's when the first derivative is 0, only when x equals 0. And when x is negative, it's negative 4 times negative. The first derivative is going to be the first derivative is greater than 0 here, so it would be increasing. And the first derivative is going to be less than 0 when x is greater than 0, because you'll have a negative times a positive, so it would be decreasing. So this is probably enough for us to graph this thing. I'm going to do this in red, and so in order for this thing levels off here, so it's going to have this is going to have a maximum, and it has these asymptotes, so this must have this kind of a shape. Now we also have this thing increasing, but not crossing the x-axis, so this must have, and to obey these asymptotes, it must do this, and it's going to be decreasing on the other side, so it's going to look like that. Of course, we also observe this thing is an it's an even function, so it has that symmetry over the y-axis. And I didn't bother going to inflection points, but in fact, the curvature is only changing when the curvature is downward curvature between -1 and 1, and it's upward curvature on the other intervals. We could find that from the second derivative, but this is enough. I don't need to go any further. I know what rational functions look like. Okay, let's take y equals x times e to the x. First off, the domain is going to be all the real numbers. And let's put in some axes for this. We got y of 0. The y-intercept is going to be 0. So we know that this is going to intersect right here at that point. This is also the only time that x e to the x is equal to 0 is when x equals 0. So there's no other x-intercepts. All right. Then let's find the first derivative of this thing. Actually, you know what we could do is let's take the limit. The limit as x goes to infinity of x e to the x is clearly infinity, like it's an infinite limit. It just is unbounded. And the limit as x goes to negative infinity is going to be, well, this is going to be infinity times 0. If you think about this, like, because e to the x goes to 0, but x is going to go to a negative infinity. So what we could do is actually write this as this is actually the limit as x goes to negative infinity of x over e to the negative x, right? And you can see that the numerator is going to go to negative infinity. The denominator is going to go to infinity. So it's a good question of where this exactly goes to. So let's use L'Hopital's rule. That's infinity over infinity. That's going to be the limit as x goes to negative infinity of 1 over negative e to the negative x. Now that's going to be 1 over negative in negative infinity. That's going to be 1. That's going to go to 0. Okay, so that's good. So we know that this thing does have an asymptote at 0. It goes to 0. Now let's find a couple other critical points of this thing. So y prime is going to be e to the x plus x times e to the x. That's the first derivative of this thing. And if you set this equal, this is e to the x times 1 plus x. So this is equal to 0 when x equals -1. So we do have well, let's look at a sign graph of the first derivative. This thing is going to, at -1, it's going to be 0, and this is going to be, let's see, when x is greater than that, it's going to be positive, it's going to be negative. So this thing is decreasing, and then it's going to be increasing. Okay, let's look at the second derivative. The second derivative is, I'm going to have the product rule again. It's going to be taking this form here. It's going to be e to the x times 1 plus e to the x, times, 1 plus x. This is going to be e to the x times 2 plus x. So this is going to be, this y double prime is 0 when x is -2. So we have an inflection point at -2. If we look at the sign graph of the double prime, -2, it's 0, and let's see, it's going to be, if you plug in, it's going to be positive and negative. So I'm going to put in a couple of helper things here. So we have at -2, -1, things are happening. In terms of the curvature, this thing has downward curvature up until -2, and then we have an inflection point, and then it's going to be upward curvature. Then we have it's decreasing and increasing is going to be it's going to be decreasing up until this point, and it's going to be increasing after that. So in order for this to happen, let's actually plot the point when x is -1. So y of -1 is negative e to the -1. So that's negative 1 over e. Roughly, e is about 2. It's about a half, roughly. So that means I'm going to plot the point -1 comma about a half, about -1/2, roughly. So I'm going to put that point right here. It's it's actually a little bit less than a half. So right around here. Okay. In order for this thing to have downward curvature but to not intersect the x-axis, it has to treat this as an asymptote. So I know that I'm drawing a little crooked, but what's happening here, it's going to go like that, but then it has to get to this point. So it is going to have a inflection point right there, and then it's going to start going up. It's going to have to hit this point, and its curvature doesn't change, so it still is going to go up, and I'm going to have it just shoot up like this. It's increasing. It's never gonna. It doesn't reach an asymptote, but it just increases. So it has this little dip. It has this kind of this curvature where it's going out to that limit. It has an inflection point at -2. It reaches a local minimum, and then it just shoots up, and the curvature doesn't change. So it's like it's got upward curvature from here, and it's downward curvature there. Okay, that looks pretty good. All right, the cosine of x over 2 plus sine of x. So let's put some axes here. We'll work on these, make that a little longer. Okay. So first off, the domain we'd only have a problem if the denominator is ever 0. But 2 plus the sine of x is always greater than 1 because the sine of x only goes as low as -1, right? So I'm not going to have any problems where I'm dividing by 0. So the domain is going to be is all real numbers. Okay. Now I can try f of 0 just to see if there's an intercept term, and this is going to, the cosine of 0 is 1, and the sine of 0 is 0, so it's 1 over 2. So it's going to be the point, I'm going to put that point as 1, that at 2, that at 3. So this is the point here. And I know that I'm going to be dealing with pi's, so I'm going to just mark these off with some pi's. This is negative pi, this is going to be negative 2 pi, negative 3 pi, and so I've got pi's, 2 pi. Okay. Now let's find the f of x is equal to 0 when and only when the cosine of x equals 0. And the cosine of x is equal to 0 at pi over 2 plus k pi. So for like at every like pi over 2, then 3 pi over 2, and so forth. So we have a bunch of points where this thing intersects the the x-axis. All right. Now this thing just keeps oscillating, so there's no limit. There's no asymptotes. So let's just take the first derivative and see when is the first derivative ever going to be equal to 0. The first derivative, if you use a quotient rule, it's going to be the sine of x times 2 plus, sorry, it's the negative sine of x, 2 plus the sine of x, plus, oh sorry, minus, the cosine of x times the derivative, which is the cosine of x. So actually what this is, and that's all over, of course, 2 plus the sine of x. Work that out. Actually, what you have is negative 2 sine x minus sine squared x minus cosine squared x. And that's all over 2, oops, I should square that, 2 plus the sine of x. Now, this squared. I clean it up a little bit more. It's negative, this is going to be negative 1, negative 1 minus 2 sine x all over 2 plus the sine of x squared. Okay, now this is equal to 0 when 2 sine x is equal to negative 1. When 2 sine x is equal to negative 1, then this numerator is going to be 0, and that's when the sine of x is equal to negative 1/2. So that numerator here, the denominator is always greater than 0, and so the numerator is going to be, let's see, the sine of x is going to be, when the sine is, let's see, let's think this through. Let's negative 1 plus 2 sine of x. When is that greater than 0? That's going to be greater than 0 when when 2 sine x is less than negative 1. So when sine x is less than negative 1/2. Okay, when the sine, so these are the angles when the first derivative is going to be positive, and so that's when that's going to be when the sine is less than negative a half. It's between those two angles. So this is going to be increasing in these intervals. That means it must be decreasing in those intervals. Now, because it's hitting the axis, I can actually say something about it then. This thing is going to come, and let's see, what's the lowest value this thing will get? Let's plug in one of these. Let's plug in, say, pi over 7 pi over 6, and just see what what's f of 7 pi over 6. That's going to be the cosine is negative negative root 3 over 2, and the denominator is going to be 2 plus 2 minus a half. So what do we have? We have negative root 3 over 2 over 3 halves. So that's going to be negative root 3 over 2 times 2/3. This is going to be negative 1 over root 3. That's roughly negative 0.58. So I'll put that around here. And f of 11 pi over 6, the numerator is going to be positive root 3 over 2, and the denominator is still going to be 3 halves. So that's going to be positive 0.58. So let's just put that dotted line here. All right, it seems to me that we have enough information to sketch this thing out without going to without going to the second derivative, because we know that this thing is going to be oscillating. It's going to be going up to there, it's going to be crossing, coming down here, crossing and going up to here, crossing, going down to there, going up to there. So it's going to be going back and forth. Now this thing is going to it goes up. I'm gonna go up and cross here. It looks like it's gonna this is the shape that I'm getting from my sketch. And here I just graphed this out to check it, and I can see I did make the mistake of not going through the y-intercept, but we did get this shape pretty well. I mean, it's got this kind of sawtooth sort of a like angular shape to it. All right. So now we're going to graph using GeoGebra this polynomial and the graphs of its first and second derivatives. And we're going to estimate the maximum and minimum points and the intervals of concavity. So let's, I'm going to okay, here we go. So you can see in red, I've got my f of x. Okay, so we're trying to estimate the minimum and point. So you can see that we are getting something here. We do have a minimum point, and if we look at the first derivative is hitting the x-axis here. It's hitting the x-axis here, and also it's hitting it right around here, I think. So these look like maximum and minimum points. Roughly, that's a min point. We have this point here. It looks like it's the origin. Of course it is. This is something, I'm not sure. And let's just figure out based on concavity. So this is the second derivative is positive. here. So this is upward concavity that doesn't change until this point here. So this is up to there. The second derivative is negative up until this point here. So this is going to be a point where the concavity changes. This thing is downward concavity. And that, since it's downward concavity, that means that at this critical point here at the origin, this is actually a maximum. It's a local maximum. And then because we have the second derivative is positive, that means that from here on we have upward concavity. And since we have upward concavity, that's actually a minimum right there. So roughly, then I'm going to say we'd have we're going to have upward concavity roughly from negative infinity up until negative 1.2. That's going to be 1.24 or so. And then it's going to go from, this looks like about at 0.2, from 0.2 to infinity. And we have downward from about negative 1.24 up until that 0.2. And yeah, that seems about right. I'm pretty comfortable with that. And if we were to zoom in, I think a little further, we can get a better sense of the coordinates of these maximum and minimum points. So here you can see, like zoomed in a little more, you can definitely see that at this point, this is at roughly, the point is like about at 0.23 is about 3. Where is that? 3.6 or so. That's because that's every 0.4. At 3.6, and what is it horizontally? This is about, that's negative 0.5, so that'd be negative 0.1 or so. This is a local minimum point. Anyway, just wanted to just demonstrate a couple of things, looking at how concavity relates to the shapes of these curves. We'll do more practice. All right, bye.